Section 1.4 is on the second type of statistical study, which are experiments or experimental studies. The way an experimental study differs from an observational study is that in an experiment, researchers apply a treatment and observe its effect on the subjects, where in an observational study, we were just observing the subjects without trying to affect them. If researchers want to determine some kind of causal connection between two variables, it's necessary to have these treatments and it's necessary to perform a fully randomized comparative experiment. When we design an experiment, there's four main principles that we want to keep in mind, and the first is control. Let's say we're testing a new heart medication. We're going to give this medication to one group of people, another group is not going to receive it. When we talk about control, we're talking about all the external sources of variation that might affect the heart rates of these groups. So we might tell both groups to keep their stress levels down, adhere to a strict diet, things like that. We're controlling as many of those influences as possible, so the only difference is the medication that they're taking or not taking. The easiest way to control is through randomization. We always randomly assign our treatment. So the people in that medication group and in the group that's not getting medication is going to be determined randomly. We don't let them self-select. Okay? And by randomly assigning these treatments, it evens out all external sources of variation. It spreads them across the different groups. So things that we've thought of and things that we haven't thought of are neutralized. The third principle is repetition. If we have more cases to observe, that gives the researchers more information. Throughout the whole course, more data is pretty much always better, assuming that our sample is not biased. And lastly, blocking. This is a principle, although it's not a required element in every design. This is when we split up our group based on some characteristics such as gender, age, that might affect the variable that we're looking at. And after we split them up, then we randomly assign our treatments to each of our groups. Now, bias can enter an experiment in a number of different ways. And one of those ways is when subjects realize that they've received a medication or they realize that they haven't received a medication. So one way that we can deal with that is by doing something called blinding the participants. Okay, and blinding is when we keep them in the dark of whether or not they've received that medication. And we do that by using something called a placebo. A placebo would look like the real medicine. Ideally, it would taste and smell like the real medicine, with the only difference being that the placebo is completely ineffective. The reason we do this is because there's something called a placebo effect, where people who are untreated are given what they believe is a medication and they report improved symptoms. So what I just described would be called a single blind design. Double blind is when the examiner, whoever is examining our subjects, also is unaware whether a subject received a medication or a placebo. Obviously, someone has to know who got the medicine and who didn't, so there's always some kind of test coordinator who has been keeping track of everything. But single blind is when one party doesn't know. Double blind is when both parties, the subject and the examiner, both don't know. Another bit of terminology here, when we talk about a completely randomized design, that's when we're assigning these treatments to our subject completely at random, such as flipping a coin, rolling a die, using a random number generator, something like that. When we have a failed experiment, it's often due to something called confounding. And confounding is when we have some kind of external variable that's affecting our subjects in a way that makes it impossible to tell if our treatment was effective or ineffective. Let's say we're testing some kind of medicine that treats the common cold. So we have one group receiving this medication, another group receiving the placebo. But in the placebo group, the person that is distributing the placebo medication to the subjects has a cold and ends up infecting all the subjects. Okay, and in the case of the actual medication group, the person distributing the medication does not. So the people in the placebo group get sick, the people in the medication group do not. Is it because of the medication, or is it because the technician who was distributing the medication was sick? That's a confounded experiment. Could also be something simpler, such as when studying whether lack of physical activity leads to gaining weight, just getting older would mean that you're less involved with physical activity and more likely to gain weight. All right, here we're going to go through some of the key elements of an experiment. So in this experiment, we're going to test the new medication for a common cold. We have 200 subjects. They've agreed to abide by a strict diet. The group is going to be split on gender, males and females. Patients who receive the new medication are referred to as the treatment group, while those who receive a placebo are called the control group. Researchers will record the length of the cold and find the average difference for the groups. Number one, how do the examiners control external variables in the experiment? Remember, when we're talking about controlling variables, we want to limit the effect of anything external to the experiment so that the only difference between the two groups is whatever medication or placebo that they're receiving. So the way that they controlled is by limiting their diets, by controlling their diets. Okay, so this is limiting any vitamin C or any other nutritional value that they might intake, which might affect the length of the cold. That way, any difference that we see can be attributed to the treatment and not their diets. Did the researchers incorporate blocking? They did. They blocked by gender. The reason that they blocked by gender is because they suspect there might be some kind of difference in how males and females react to the medications. Maybe this medication is more effective on males than it is for females or vice versa. So by splitting them up by gender at the start and then randomly assigning half the males to the treatment and placebo, and then same thing with the females, we'd be able to see those differences when it came to the final comparison across genders. Randomization was incorporated by picking names out of a hat. And that makes this a simple random sample. As to why they incorporate randomization, randomizing takes known and unknown sources of variation and spreads them equally across the groups. Okay, there's a lot of different things that can affect these subjects. And let's say instead of randomizing, we decided to do a convenience sample. The first half of the men to show up will receive the treatment, the medication, and then the remaining half will receive the placebo. Well, maybe they're showing up early because they were up earlier. Maybe they go to sleep earlier as well. In other words, their sleep cycle is more defined, it's better, and because of that, their immune system is better. Okay, it's not something that we know to be true, but it's possible for sure. So randomizing takes those things out of the equation and spreads those differences equally across both groups. The replication is just the fact that we've done this across many subjects, 200 in this case. Half of them receive the treatment, half are the control group.